All right, so we got our skeletal framework mapped out, setting us up for looking at the key resonance contributor. Remember, meta didn't have one. They're all the same because the positive charge never landed on the carbon that had the original group, which was the nitro. And ortho and para did. So let's just work those out first, because believe it or not, that makes it easier, because we know that. That was the aha moment, the emoji wow, right? Those are the ones we care about. Because you realize one of my favorite ways to approach these is to say, can it be ortho or para? In other words, can the nitro help that positive charge when it lands on that carbon? So that's the question we'll be asking. Okay, so what that means is if it's ortho, our bromine went here. If it's para, our bromine went there. If it's meta, our bromine went there. So the pi bonds had to be there and there, because if it was ortho, we use this pi bond to attach the one set of electrons we used to attach the bromine, and then that means this lost it. If it was para, our pi bonds have to be there and there, because the bromine, once again, didn't get those electrons. That bromine carbon didn't get them. Okay, meta, we could choose any of them because we're not specifying how important it is to have the carbocation here, because it never lands there. It never goes there. It only goes adjacent. That's the best you could do. So pick any one that's adjacent. Let's go here. Then our corresponding pi bond would be there and there, because it never lands on the new group, the carbon with the electrophile, or the carbon with the carbocation. All right, so what we want to say is ask ourselves a question. Does the nitro help carbocation? If yes, then we go ortho-para. If no, then we go meta. Okay? Because if yes, that means it's right next to it. But let's take a close look at that. Here's our carbocation, here's a nitro. Yuck, two positive next to each other. That's actually really terrible. So very destabilizing. I'm going to emphasize that right here. All right, it's actually one of the worst you could get, so I might even do that. So very unstable. So no ortho product. Same product here. Let's make him mad. Unstable. So did not pass this test. So did not help, so therefore it's meta by default. Meta doesn't make it better. Look, see how meta is it's not helping it, but the carbocation is not as unhappy. Carbocation is just secondary, but it's not attached to anything that makes it even more electron deficient like the nitro would. So stay away from the nitro if you have a carbocation, which means meta is the only way to go. Okay, so when we have the summary, when we have electron withdrawing groups, we will have the meta product only. Okay. Other meta directors to watch out for. There's a lot, actually. Let's throw them in here. We have anything that you've ever learned was an electron withdrawing group in the past. So I know these have come up. It doesn't have to be fluorine. That's a popular one. It could be other halogens like CBr3, right, or CCl3. Nitro, since we've already covered that. Another positive charged one is ammoniums, which can have an R or an H bound to it. They're still, remember, amines are NR3 or NR2 or NH2 or NHR, or NH2. So we have all the different possibilities. You can interchange those R's and H's, but because we have that positive charge, we have less electron density on the end, and lone pair is not there. That makes it electron withdrawing. Various carbonyls, or Y could equal, think of all the carbonyl functional groups you know. OH, R, OR, H, NH2. Let's see. Nitrile is electron withdrawing. Sulfonyl. called SO3H. That's electron withdrawing. As you can see, the pi bonds make it kind of similar to carbonyl. All right, so all metadirectors are easy to spot because they are electron withdrawing groups. That means they are also deactivators. Okay, that's simple. There are no metadirectors that are activators. Unlike the orthopara director, which happens to have the strange cousin deactivator in its family, the halogen. Let's summarize this all just so we can recognize them, because we're going to be throwing the benzenes at you with the groups on them, and you're going to have to stop and think and say, okay, is this activating the ring? Is it deactivating the ring? And this is the kind of table you might need to rely on at first, but the idea is you'll do so much homework, I hope, in practice, that this will start to come naturally. You'll recognize them. And it's easy to spot them when you see what their key features are. So here's how the table's organized. Klein has a similar one I really like. You could look at that as well. We're going to start with very strong activating ability here. So let's shrink this up and summarize that spectrum here. So this means most reactive benzene, it's activated. You can increase the reaction rate. This is where we have the least reactive benzene. And then right in the middle here is H. Okay, so it's neither activating nor deactivating. Okay, so keep that in mind. That's what we're comparing here. All right, so activators. Let's look at examples first. The strongest activators we'll see, and if you look at lots of different books, they might have a little slight disagreement about which one of these two they go to or these two, but overall trend in predicting the products will stay the same, so don't be too concerned about that. But I think Klein and I agree pretty well on that one. NH2 amines, as well as NR2, or HR. So the amines. The squiggle means that's the point of attachment to the benzene ring. So it's directly attached. Alcohol, phenol, or ether. Phenoxide, even more so. Directing effect, orthopara. Why? Lone pair is adjacent to the ring. We saw that with the resonance. It's with the anisole version. It stabilizes, it helps that carbocation. That was our question, right? Will it help that carbocation? Yes, that lone pair to the rescue by resonance stabilizes it. Now, some of these have their lone pairs, it gets complicated. Their lone pairs get tied up. They're not as ready to donate electron density, but they're still there. That would be the amide case, where the nitrogen H is attached to the ring, but on the other side, there's something a little electron withdrawing, like a carbonyl. Or an ester attached at the O. At first, it looks electron withdrawing until you donating until you draw on that carbonyl, and you say, oh, well, it's got some business on the other side pulling away at competing with it, but it's still considered a moderate electron donating group. So I'll write that explanation in the words I just said out. Lone pair, still adjacent, to ring, but attached to EWG. Okay, now still an activator, still an orthopara director is our first example. Alkyl groups. R groups, they could be alkyl or aryl. Remember AR is short for aryl. So those are weakly activating. That's because they don't have as significant effect as resonance. Hyperconjugation helps that carbocation, because remember we're asking the same question. We look at the sigma complex, we find the carbocation, we ask, can the group attached help that carbocation? Alkyl and aryl groups can help it. Yes, that was our first example with toluene. So hyperconjugation can do the job there. So it will make the reaction go faster than just an H alone, which can neither help or hinder the speed of the reaction, because that's our baseline. Let's take a look at what it takes to be deactivating. So remember, I'm going to actually work at the bottom, because the extremes are the most obvious. So strongly deactivating, slows down the reaction significantly, is something that's a strong electron withdrawing group. It's going to be a meta-director, and that would be our friend the nitro group we just used. Others that can fall in that category, strong enough to do that, are, oops, get back there, CF3 or CX3, and the positive charged ammonium. Strong electron withdrawing group. You don't really have to be too concerned about the difference between each of those. The internal ranking, just know that they fall in the strong category. They're stronger than what comes before them, which is moderately electron withdrawing. Usually, to be moderately electron withdrawing, they have a pi bond adjacent to the ring. So you can spot them. So adjacent. So you can imagine the ring electrons can leave when the pi bond opens, so thus pulling electron density out. Who does that the best? These carbonyls. Aldehydes. This time I'll draw more of them out. Ketones. Esters, but be careful, esters connected the other way. We drew esters on here already. If esters connected at the oxygen to the ring, it's electron donating. If it's connected at the carbon of the carbonyl to the ring, it's electron withdrawing, right? Because it sees the carbonyl first, not the lone pair on the oxygen first. So flip the ester around, you change its electron directing ability. Carboxylic acids. Watch out for amides too. They can have the same sneaky fate there. You can connect the nitrogen to the ring and have an amide still. So amides two ways. When amides are connected at the carbonyl carbon, they're electron withdrawing. Okay, the only two that aren't carbonyls. Sulfonyl and nitrile. But they're similar because they have the pi bonds, right? Adjacent. Okay, let's get to the weird one in the family. Every family has one, right? Might be me and my family, actually. No, I shouldn't say that. My family's nice. But I guess I wouldn't know if I was. Deactivators. They're still important, right? They're playing a role, a niche role here. They are strange because they are below this line. They slow down the reaction, yet they are the only ortho-para-director that slows down the reaction. These are the halogens we spend a whole page on. So they have reasons for that. Remember, the strong dipole makes it an electron withdrawing group, but resonance simultaneously made an electron donating group. So that conflating sort of concept going on there. Those have that tug of war where it kind of put it in the middle of the spectrum. So watch out for chlorine and bromine. We don't really play with fluorine as much. It's just not very cooperative, very reactive, and not very fun to deal with. Iodine's actually pretty useful in a lot of other reactions, but we don't use it in most of these aromatic substitution reactions. So just chlorine and bromine are what you need to keep track of for this chapter. So this is the weirdo. Watch out for that one. Okay, so how does this come into play? we've kept it kind of simple where we might say, hey, there's something already on the ring, we're going to put one more thing. But we're going to be starting to get to multi-step synthesis. So we'll get there slowly. Let's just do a two-step instead of a one-step. So we've been doing one-steps all this time. What's the mystery director? So we've only covered 2 of the 5 electrophilic 5. So we know we have to use these 2 reactions, bromination, nitration. However, which one do we do? The order really matters. Why does it matter? Let's just take a stab at it, see what happens. And when in doubt, there's nothing wrong with some trial and error. Let's compare nitration first. So nitric acid with sulfuric acid is step 1. So you get the nitro on first. Step 2, Br2, FeBr3. Versus 1. You know what I'm going to do just to clear that up? Let's do that stepwise. Okay. 1 nitro. Let's do 1 FeBr3, Br2. Okay, so let's try to bring it home. Let's wrap up this one with a nitration. Nitric acid, sulfuric acid. Bromine was already on there. Now we have to say, okay, what does bromine like to do? Look at the chart. Bromine is, he's off the chart now, an orthopara director. We have to go orthopara. We don't get a choice. So we can go here, here, or here. Because we're looking at that, and that tells us that we have to go ortho or para. So we kind of got ourselves in a pickle here because our product is actually meta. So this is not going to work, is it? I don't think we need to keep going. Scratch that. Nitration first is a bad idea. You put on, oh, what did I do? Yeah, bromination first was a bad idea. Nitration first might be a good idea. So we're going to scratch this route. I'm going to keep marking it off. So let's see if this one's more promising. Nitro. Let's add the bromination step. 1 FeBr3 and Br2. I don't even need a 1 because I'm not doing that, so this is actually my second step. All right, so nitro. Look at our table. You might remember it's a meta director. Bingo. That'll get us to the product. So here, we're good to go here. So our final synthesis is step 1, nitration, step 2, FeBr3, Br2. The wrong synthesis would be the reverse order. Step 1, bromination, step 2, nitration. So the moral of the story is, watch out for the order of the reactions. Beware. Beware of the order of reactions. Are you ready to level up? I think so. This is where it really gets fun. It becomes almost like a little strategy puzzle. We are going to find out what happens when we start with 2 things on the ring. Where do we put the third? So when we have that coming out the middle, remember, we don't know if that's ortho, meta, para. Okay, so it has a choice of being ortho to X or Y. Okay, when we have a di-substituted benzene ring, like we do here, di-substituted, and we're going to make it tri-substituted, we have to evaluate sterics and electronics of the 2 groups attached in order to determine where the new group goes. Okay, so let's give that a try. Let's see if we can keep that in mind. We're going to chlorinate both of those guys down there, this one and this one. Let's start with the first one. Where does that chlorine go? Methyl at the top, nitro at the bottom, that doesn't change. You might say, oh, great, who do I pay homage to, this nitro or the methyl? Who wins? Who's the boss? Who tells the chlorine where to go? Remember our chart. We're going to go get it because we'll be pulling that out a lot to do the homework. Here it is. Who plays the biggest role on benzene ring reactivity? The biggest activator. So if something's most reactive, it increased the reaction rate. That means we're in the activator realm. Activators always win because they dictate the reaction rate. It is because of them that we have the reactivity that we do have. So what if we have two activators? What do we choose? Well, they better be in two different categories here because that's the only way. If they're in the same category, then we don't know. So they will be different, okay? And honestly, that's pretty obvious, like lone pair only, lone pair next to pi bond, hyperconjugation only. It's one of those three realms for those activators. All right, let's go back and with that in mind, see if we could find the most activating group. Okay. NO2 versus methyl. NO2 is very deactivating, strongest deactivator there is. Methyl is weakly activating. Therefore, methyl wins. Ignore nitro. Because remember, the carbocation is going to be stabilized by the ortho-para position of an activator. That's all that matters. So because this is an activator, it wants to put in an ortho or para new group. Para is taken. It's not an option. Para is the only, ortho is the only site available. So we know it's an ortho-para director, and it can't go there because it's already occupied. So it doesn't matter which side I pick, it would be giving me the same product out of symmetry. So I'll just pick it here and we only get one product. Okay. Let's do that again. Electron donating, ether, electron donating. Methyl, we already established, weakly electron donating. Uh-oh, both electron donating, but we know that alkyls are the bottom of the rung. In terms of the hierarchy, there's a pecking order. Ethers are at the top. Therefore, this is a winner. It wants to be at the para position, which it can't be, or the ortho positions, which it can be. So it ends up ortho, instead of to the methyl this time, to the ether. Okay, so rule number one is an electronic effect. The most activating group dominates. It's usually EDGs. Now, what if they're exactly the same? Will there be a preference? So there's two groups. Let's say we want to know where the chlorine is going to go. So methyl, methyl, where does that chlorine go? Well, let's just look at one of the methyls. We know that it's an EDG. It's weakly activating. It wants ortho, ortho, or para. Now let's try that for this. So that was this one. Let's try it for this one. Let's make this one green. Ortho, ortho, or para. So they all coincide with the same desired placement. So we can also say these are the same by symmetry. If I put the chlorine at this one, it's the same as if I put the chlorine there by symmetry. So I'm really asking, is it going to go here or here? Well, if we draw in all those H's and note that methyls are actually got a little steric bulk to it. And we imagine which carbon has more space for a group to come in. Electronics are the same now. Now we look at sterics. There's less room here than right here. Right? Sterically hindered. So the major would definitely be one of those two on the exterior. I'll put it here just because I have space. So rule number 2, it's 2 rules only, minimize steric hindrance. So most of the time you're going to be asked for major products because we don't always want to draw all 10. We want to know what's going to be the most dominant product because that requires some brain power too to reason through it. So you could draw everything possible, but if you were asked to draw the major product, that doesn't help, right? It's not the right answer. You need to have the major product. Okay, so I'll just write major. Methyl's not huge enough that I guess it would be impossible to get in there, but you can have more extreme examples. So if you see isopropyl T-butyl, that's screaming sterics, and stay away from that spot no matter how favored it is electronically. So that's how you get to the extreme end of the steric spectrum. And you will often have to use both rules simultaneously, rule 1 and 2. So let's look at this example. 2 groups attached. One is electron donating group. One is an electron withdrawing group. Therefore, electron donating group wins. We don't even consider the blue. We don't care that it wants to go meta. We are looking only at the black. Okay, the black one wants to go ortho. Oops, I don't want to use the blue. That'll be confusing. Ortho or para. Well, T-butyl is huge. That's our token too big of a group that's too big. When you see T-butyl, think about sterics. Anything bigger is like screaming sterics at you. So T-butyl is always sterically hindered. So it blocks the closest sites. So we're not going to pick those. That'll be the favored one, the one farther away. It's smaller than a carbonyl. So we're going to favor as our major product. Here's our T-butyl. You can just write even TBU sometimes. Here's our original acyl group. New group is chlorine. Okay. Feel good about that, I hope. That's when it gets fun. And it's hard to believe we're doing that with just knowing 2 reactions. We have 3 more to do. So before we do more synthetic strategies, because we are far from done, let's do the next reaction. Introduce a new reaction. Sulfonation. So we want to get a sulfonyl group on there. Here's our reagents we need. SO3 gas, H2SO4. And I'm going to ask, just for the sake of it, would we get ortho, meta, or para, just because we always want to practice that. Okay, so notice this is electron withdrawing. We're always going to start with the substituted ring so we can keep practicing that effect as well. Sometimes we'll have an electron donating group on there, but since we have an electron withdrawing group, in this scenario, it's going to only favor meta, one of those 2 positions. So following that model, okay, so what's our electrophile? We have SO3, it's actually a gas in there. How did that turn into SO3H? Let's look at that. This is the Lewis structure of SO3. And we have our good old sulfuric acid. Simple acid-base reaction. let one of those lone pairs get protonated. Sulfuric acid, you see that, you should just say, how's it going to be an acid? What's it going to protonate? Well, we see that. I drew in those lone pairs. That's kind of a dead giveaway, right? There's our SO3H. Okay, so when a pi bond attacks that S, it says, thank you so much. I can give those electrons back to oxygen, and we're all happy again. So that's the driving force for that. That's our electrophile. Circle him. There's our electrophile. Okay, I'm going to draw how we use that electrophile. I'll let you finish the mechanism because we've been doing that. As you can see, it's an important mechanism. So pi bonds, acyl group, plus SO3H. Just draw our SO3 and then let one of the O's have an H on it. Positive charge. That's our electrophile. That's the one that is going to be happy to be opened up. Okay, so since we need to go meta, thanks to this guy, and that's not a sulfonyl particular thing. Remember, we could have had a methyl group on here. We would have gone to ortho or para. This guy's telling us we need to go meta. So we've got to pick the bond that's already a meta. So it could be this one, it could be this one. I'll pick this one since it's a little closer. I'm going to reach over here and attack that sulfur and open up the pi bond. This is my rate determining step, by the way, RDS, forming the carbocation. Leave those other pi bonds alone. I'm just drawing in the framework. Time for the new part. Carbon that's ortho gets the carbocation. Carbon that's meta gets the new group. There's SO. OH, that's SO3H. Okay, then you could work around the ring to show the resonance, etc., but that's how it gets in there. I'm going to let you finish, okay? Sulfonyl group is weird looking, right? I mean, this is the first time we've decided to really use it as a functional group, other than maybe it looks something like what we see in sulfuric acid. Why in the world do we want to put a sulfonyl group on our benzene ring? I mean, nitro you could probably understand, halogens, but we have not been using sulfonyls left and right. There's a reason. It's actually got, you know, a good synthetic strategy. And a lot of organic chemistry can be thought of as like chess or a jigsaw puzzle where you need just the right move to accomplish your goal. And sulfonyl group is kind of a key player sometimes. It can actually be used as a blocking group. So we might not actually want a sulfonyl in the end. We just might want to block a spot. Why is the sulfonyl group a blocking group? It's reversible. It's a reversible reaction. So the whole reaction, go back to that, up at the top deserves this addition. It comes off. How do we get it off? H plus and water to remove. So it's reversible. All right, so note that means there is no water available here. Sometimes this is even referred to collectively, SO3 mixed with H2SO4, as fuming sulfuric acid. So if you see that over the arrow, that means it's going the forward direction. That's the same as writing SO3, because it's a gas, that's the fuming, right? Fuming sulfuric acid. Super concentrated. No water. Why? Water helps reverse it. Okay, so that reversibility is unique to our electrophilic 5. It's the only one that we're treating as easily reversible. So we can exploit that and take advantage of that property. Look at this one, for example. We just learned that T-butyl is huge and would always prefer para. And yes, it would. Let's suppose we want to do a synthesis where we really want to get ortho. We don't want to get para. Stomp my foot. No para, I want ortho only. Well, that's okay. We can actually do that thanks to sulfonal. If we put sulfonal on, it'll go para because that's all that is really preferred. And then very reluctantly, we can get a small group in there like chlorine. Remove the sulfonal, and then we're home free. Okay, so let's write that out. So H2SO4, SO3. That will give us para only. But it's temporary. We're using it as a blocking group. So I might circle that and point that out. It's like you never knew it was there. Right? It's like a secret tool. Then we install the chlorine. So we have, T-butyl says, I don't want to put you ortho because I'm too crowded already, but chlorine says, too bad, somebody's already at the para position, so here I come. Now, we tricked you, haha, we can remove with acidic water. Pick an acid, we'll use sulfuric acid just because that was likely handy since you just used it. So the whole goal of that, so this was block, para position, and this was remove the blocking group. So what else is that useful for? T-butyl, isobutyl, isopropyl. So other sterically hindered groups. I mean, I can't list them all because I could invent a whole ton of them. But if you see like a ring, right? And I'm just going to write like that because it could be any numbered ring. It could be a hexagon, pentagon. So a ring, I'll put N ring so we can keep that general. It could be isopropyl, that sort of branched, immediately branched sort of shape. T-butyl, of course. So, but then we have so many variations on branch. It doesn't have to just be T-butyl. It could be going that way. So those, watch out for that pattern though. Notice they all have that in common. Where at the first carbon that's attached, there's branching. Those are usually the classically too sterically hindered to allow ortho in, and para is strongly preferred, but not impossible to get ortho. It's just para is very strongly preferred. So you can block the para, squeeze in the ortho, take the para blocking group off. Chemistry, chemistry, chemistry.